In this video, we're going to introduce the double and half angle identities for the sine and cosine functions. To discover the double angle identity for sine and cosine, we're going to start with the sum identities, shown here that we've previously seen, and we're going to let a equal b in both of these identities. And so in particular, if I replace all of the b's with an a in both of these identities, we obtain this, which we can then simplify. Sine of a plus a will become sine of 2a. And on the right-hand side, we see that we have two terms here. We have this first one, which is sine a cosine a, and the second one, which is sine a cosine a, which are the same exact term. And so when we add them together, we get two copies of those, or 2 sine a cosine a. In the second equation, we have cosine of a plus a, which is cosine of 2a. And here we have cosine of a times cosine of a, and that is cosine of a squared, or cosine squared of a. And the other term that we subtract here is sine a times sine a, which is sine squared of a. So these are one version of the double angle identity for sine and cosine. Sine of 2a, double the angle a, is 2 times the sine of a times the cosine of a. And the cosine of 2 times a is the cosine squared of a minus the sine squared of a. This is the only version for the sine of 2a, but the cosine of 2a has a couple additional versions which are sometimes helpful. Recall, for example, that the cosine squared of a can be written as 1 minus the sine squared of a. This is using the standard Pythagorean identity. If this is then substituted in to the cosine of 2a formula we have here, we obtain another formula when simplified that will give us a 1 minus 2 sine squared of a. So this is another version of the double angle formula for cosine. Right? And likewise, we could substitute sine squared a in as 1 minus cosine squared a using the same Pythagorean identity. And this would yield cosine of 2a equals 2 cosine squared a minus 1. So this gives us 4 identities involving the sine and cosine of a double angle, 1 for sine and 3 for cosine. In this example, we would like to find the sine and cosine of 120 degrees. First, notice that we could do this problem without using any of these identities, as 120 degrees has a reference angle of 60 degrees in the second quadrant, and so we can use reference angles and the sine and cosine of 60 degrees, which we know, in order to do this. However, for this example, let's use the double angle identities to illustrate how they can be used. So to do the sine of 120 degrees, for example, the first thing that we want to do is recognize what 120 degrees is double of. In particular, notice that it is 2 times 60 degrees. And so we're going to apply the double angle identity for sine with a equaling 60 degrees. And so the formula for sine of 2 times an angle a is 2 times the sine of that angle times the cosine of that angle. So in this case, 2 sine of 60 degrees, cosine of 60 degrees. We can simplify this, of course. 2 sine of 60 degrees is the square root of 3 over 2. And the cosine of 60 degrees is 1/2. And so here the 2 and the 1/2, for example, might cancel. And so what we're left with is just the square root of 3 over 2, which is the sine value of 120 degrees. We would have also obtained this if we used reference angles. We knew that's the same as the sine of 160 degree. The sine of 60 degrees, and the same sign because in the second quadrant it is positive. Our second part here is we want to find cosine of 120 degrees. Again, this is going to be cosine of 2 times 60 degrees. And so we apply this formula we apply any of the formulas for the cosine of twice an angle. For example, we could use the first one we had, cosine squared of 60 degrees minus the sine squared of 60 degrees. So the cosine of 60 degrees is 1/2, so we want 1/2 squared. Minus the sine of 60 degrees is the square root of 3 over 2, so we want to subtract square root of 3 over 2 squared. And this becomes 1/4 minus 3/4, which is negative 1/2. And again, we know that is the cosine value of 120 degrees because the cosine of 60 degrees is 1/2, and in the second quadrant, cosine is negative. If you would have used either of the other two identities for the cosine of 2 times an angle A, you would have also obtained negative 1/2. And so those three formulas can be used interchangeably. For another example involving the double angle identities, suppose we have an angle theta in quadrant 2, and we know that the tangent of theta is negative 2/11. We'd like to use this information to find the exact values of sine of 2 theta and cosine of 2 theta. In this example, we are not going to find the exact value of theta, but rather use the given information about the tangent and the quadrant of theta to find the sine and cosine of theta, and then use the double angle identities for sine and cosine of 2 theta. So here we have we're given an angle in quadrant 2, and so and we're given the tangent of that angle. And so that allows us to draw a right triangle in quadrant 2 and identify 2 of its sides. Tangent is opposite over adjacent, so the opposite side can be 2 and the adjacent side 11. So we obtain a triangle like this. We can then find the third side of this triangle by the standard procedure of using the Pythagorean theorem. So 2 squared plus 11 squared equals h squared. And so that means 4 plus 121 will be h squared, which will be 125. And so taking the square root, we see that the hypotenuse of this triangle will be the square root of 125. And so from this, we have that sine of our angle theta is going to be the opposite side of 2 divided by the hypotenuse of square root of 125. In this case, that will be a positive value because in the second quadrant, sine is positive. And our cosine will be 11, the adjacent side over square root of 125, the hypotenuse. But this will be a negative value because in the quadrant 2, cosine of our angle will be negative. And so while we do not know what angle theta is, we do know its sine and cosine values, which will then allow us to be able to find the sine and cosine of 2 theta. So for the sine of 2 theta, we apply the double angle identity, and we see that this is going to equal 2 times the sine of theta times the cosine of theta. And we know both of these trig functions. We know that sine of theta is 2 divided by the square root of 125. And we know that the cosine of theta is negative 11 divided by the square root of 125. And so we just need to multiply all of these quantities together. In the numerator here, we end up with 2 times negative 11, which is negative 44. And in the denominator, we have the square root of 125 times the square root of 125, which is 125. And so sine of 2 theta will be negative 44 over 125. For the cosine of 2 theta, we actually have some choices. There are 3 formulas that will help to compute this. For this example, let's go ahead and use the formula that cosine of 2 theta is equal to 1 minus 2 sine squared of theta. So here we will substitute in the value for sine of theta, which we know is 2 over the square root of 125. And so we obtain 1 minus 2 times 4 over 125 when we square that, which is 1 minus 8 over 125, which becomes 117 over 125. And so this will be our cosine of 2 theta, and negative 44 over 125 is our sine of 2 theta. And so we've obtained both of these particular values using our formulas and the sine and cosine of theta. Notice here that the sine of our angle is a negative number, and our cosine down here is a positive number. And so if we put these two facts together, we have a negative sine and a positive cosine. This tells us that the angle 2 theta is going to be in quadrant 4. This is the quadrant in which sine is negative, yet cosine is positive. So again, without knowing anything about theta other than its tangent value and its quadrant, we're able to figure out the sine and cosine of twice that angle, as well as figure out the quadrant in which that angle lies.